Most retrieval-augmented generation pipelines fail because they rely on a flawed assumption that mathematical proximity in a vector space guarantees contextual relevance to a user's query. In a standard single-stage RAG setup, a user inputs a query. That text is converted into an embedding, and a vector database scans its index to find the documents closest to that query in the dimensional space. This system is built to search millions of documents in milliseconds. But to achieve that speed, the database evaluates candidate chunks based on raw mathematical distance, completely ignoring the nuanced meaning behind the words. By prioritizing high-speed retrieval over semantic precision, the database floods the large language model with highly irrelevant, noisy context. The root of this noise lies in the core architecture of single-stage retrieval, the bi-encoder model. This diagram shows the bi-encoder mechanism. The query goes down one path and document chunks down another. They are compressed into standard embeddings independently, never interacting. This architecture allows high-speed search. You pre-compute embeddings and rapidly compare the query against thousands of chunks simultaneously. But fetching a broad set of candidates quickly has a cost. You are passing dozens of loosely related text blocks into the strict token limits of the LLM. When you feed an LLM this broad data, information that is mathematically proximal but contextually weak, it dilutes the model's focus, degrading the accuracy of the final generative output. To maximize a strict context window, production pipelines have to physically decouple the fast, broad retrieval from the slow, deep semantic relevance scoring. The structural solution to the independent encoding trap is adding a second stage to the pipeline, a re-ranker. This cross-encoder schematic illustrates a mechanical shift. Instead of keeping text separate, a re-ranker takes the original query and retrieved document chunk, fusing them into a combined input. Passing them together through a unified transformer block enables deep token-level interaction within a single pass. Where a bi-encoder relies entirely on spatial distance to guess relevance, joint encoding forces nuanced relationship mapping. It identifies context, negations, and complex phrasing that spatial metrics miss. This two-stage approach divides the labor of retrieval. The database performs the fast, broad fetch, and the re-ranker performs the slower, exact evaluation. By scoring relevance through deep interaction, you improve the final ranking quality, ensuring only the precise chunks survive the filter. Every re-ranker implementation forces an optimization trade-off between retrieval accuracy and infrastructure cost. This matrix plots nuance and accuracy against computational overhead and latency. Deep query chunk interaction introduces heavy processing costs. Engineers must balance this trade-off matrix against strict latency budgets, targeting high accuracy without stalling the system. For highly interactive, real-time, or high-traffic applications, processing dozens of fused text blocks through a transformer is entirely unscalable. The success of a two-stage pipeline depends entirely on selecting the specific re-ranker architecture that fits your use case. The baseline model for the second stage is a standard cross-encoder. Looking at the matrix, cross-encoders plot high on accuracy, producing precise relevance scores based on detailed mapping. But this point sits far to the right. The high computational cost rules it out for applications requiring ultra-low latency. To solve this, engineers use a second architecture designed explicitly as a structural compromise, multivector or late interaction models. Colbert is the leading example of this late interaction approach. Colbert returns to encoding the query and chunks separately to save compute at runtime, but instead of relying on a single vector distance, it performs fine-grained mathematical interactions between multiple vectors after the initial encoding. This places late interaction models right in the center of the graph. They balance high performance with lower compute costs, making them highly effective for production systems. Beyond those two options is the final, most resource-intensive architecture available, the LLM Re-Ranker. This approach plots at the absolute extreme. It utilizes a generative large language model to logically reason about relevance, moving past mathematical attention into semantic deduction. This achieves unparalleled accuracy, but incurs massive, prohibitive computational overhead. You only deploy this for highly specialized asynchronous tasks, where accuracy is the absolute highest priority and latency is not a concern at all. Across these three models, there is no universally superior choice. There is only the correct mathematical alignment to your application's latency and accuracy requirements. This pipeline schematic shows the two-stage paradigm. The by encoder retrieves a broad net of candidate documents, passing them to the re-ranking module. Here, the re-ranker acts as the ultimate gatekeeper. Out of 100 matches, it filters the flow down to the highest scoring few. Restricting the data flow to only the highest fidelity information drastically reduces the chance of model hallucinations and tightly focuses the LLM's reasoning. Without this gatekeeping step, the generative capability of your final model is constantly throttled by the noise of broad, single-stage retrieval. This two-stage architecture shifts the system toward active relevance modeling rather than simple index lookups. Ultimately, model selection is your primary lever for pipeline optimization and cost control. If you are building a system that requires speed and cost efficiency at scale, deploy multi-vector late interaction models. Reserve LLM re-rankers or strict cross-encoders for specialized use cases where perfect precision justifies the latency tax. Mastering retrieval-augmented generation requires moving beyond simple embeddings. You have to structurally architect the smartest possible interaction between a query and its context. In modern Gen AI applications, engineers mathematically construct relevance.